Okay, so good afternoon, everybody. Thank you for participating, and thank you very much, Larry, for giving me this opportunity to present my research as part of MATC. So just a very short introduction about myself. I'm a faculty in the Civil Engineering Department at the University of Iowa. I am specifically part of the Water Resources Group, and my research is conducted in what we call the Iowa Institute of Hydraulic Research. And most of my research is numerical, and I'm doing lots of research related to several aspects of flow and transport in rivers, in particular turbulence, shallow flows, some eco-hydraulics, and lots of stuff related to sediment transport. And in particular, I'm very much interested to understand the fundamentals of sediment entrainment and sediment transport in rivers, and in particular in rivers containing hydraulic structures. So because my research is mostly numerical, what I am trying to do is to, in many cases, replace the data which will normally come from flume studies, from scale model studies in the laboratory, by basically some kind of numerical experiments, and then to use the data in order to answer some questions of engineering interest. And I hope that the research I'm going to present today is going to be a good example of that. So this being said, let me share my screen so that you can see my presentation, and we can start. My research today is going to be related to the development of some improved design guidelines for riprap sizing protection against erosion at wing wall and spill-through abutments, which are two of the most popular type of abutments which are used at bridges. I should also mention that most of the work I'm going to present today is due to Hao Wu, who is basically my PhD student. So with this, let me start with a little bit of motivation. Of course, maintaining our roads operational is of great economical importance, and the state DOTs are in particular basically focused on this task. And in order to achieve that, we need reliable and safe transportation infrastructure design. Of course, in the case of bridges, bridges are critical elements of road networks. So if a bridge has a structural failure, okay, then it means that the road is not going to be operational, at least for a couple of weeks or several months, until that structural problem is not going to be addressed. So the question is, when do those structural failures typically occur for bridges? And the answer is they typically occur as a result of very large floods and of other hazard situations, but mostly it is related to floods. And why is that? Because once a flood will occur, the velocities, the discharge, and the water elevation inside of the river are going to increase. And that's true in particular at the location of the bridge site, okay, where you also have a contraction of the flow and an acceleration of the flow near everything which basically supports the bridge, which are the bridge piers and the bridge abutments, okay? So as a result of that, you are going to start developing lots of erosion around these hydraulic structures. And at a certain point, you may have a situation in which the foundations of these abutments and piers start becoming exposed. And that is basically the main cause for developing structural failure problems at bridges. So let me give you an example of that. And here we have relatively medium-sized bridge, and you can see that the bridge really collapsed. And again, the reason why this bridge collapsed is because of severe local scour developing near one of the abutments in this case. And again, the scour is by far the primary reason for bridge failure, not only in the United States, but in fact all over the world. Now, another problem is related to bridges is that not only the bridge piers and the bridge abutments can basically fail, you know, if they have too much scour around their foundations, but especially at small bridges, the embankments of those bridges are basically built from erodible material, okay? And again, at high flood conditions, when you have started having water in contact with the embankments, you may develop lots of erosion. And you can see a very nice example in a way here, sorry, where basically we have a small bridge in Iowa. This is what we call a wing wall abutment, which is basically, its toe is basically built of reinforced concrete, so it cannot basically erode, it can fail via scour beneath it. But then you can see that all the embankment was washed out by the flow, okay? And then you can see when they rebuild the bridge, basically you can see the embankments now are basically put back, so to speak. And also you can see the scour protection measure, they basically put larger rock, so riprap stone, over the lateral faces of the abutment in order to protect it in the case of a large flood, when basically the floodplains becomes inundated. So now let's talk about how we can basically protect the bridge abutments and the bridge and their embankments around erosion. Now, there are many methodologies which can be used to protect bridge piers and bridge abutments against local scour, but placing rock riprap around the base of these hydraulic structures is by far the method of choice, because it is relatively easy to do and it is less expensive compared to other methods, okay? So we are going to basically focus on protection of bridge abutments against a local scour using rock riprap. Okay, so basically, what do we have to do? So let's say we have an abutment, you see my cursor here, and where are you going to have the largest mean velocity in the flow, which also means the largest bed shear stresses, where it is going to be in the region where the flow accelerates, and typically that happens around the base of the abutment, especially that also the flow contracts in the bridge section, because the whole cross section is going to diminish as basically because the abutments extend for some distance over the floodplains, and also you have the piers, okay? So now what is the main modes through which the rock riprap is going to fail? This mode of failure is called shear failure, and it is really related to the fact that at a certain point the flow velocity over the region where we dispose that rock riprap is going to be sufficiently high such that basically the flow is going to start is going to start ejecting into the flow some of those stones, okay? And the main design question is, given certain geometry of the abutment of the river channel, and given some flow conditions, meaning what is the mean velocity, the discharge, and the mean flow depth, what should be the minimum median diameter of the riprap stone such that any of the riprap stones is not going to be entrained by the flow, meaning shear failure is not going to happen. Now, there is a secondary question, which is, besides the minimum riprap stone, what should be the area and the position of the region where do we have to put this stone? Typically, this is a much easier question to answer, and there are some very good recommendations on what should be the surface that should be covered by rock riprap. But the main design question is, what should be the minimum median diameter of the stone which we need to put inside of the apron, okay? Now, this is a question which in terms of, which basically was a big research topic starting in the 50s. One of the first design formulas was due to Larson and Toch. And after that, you know, there are many, many formulas, lots of publications, many NCHRP projects basically supported by the federal DOT. And basically, in fact, at this point, we have many formulas. We have lots of data from flume experiments based on those, based on which those design formulas were calibrated. And in fact, two of them are adopted in the present guidelines, which are used by the state DOTs. And this guideline is called HEC 23. Okay. Now, what is the problem with the existing design formulas in the guidelines? Well, those design formulas were applied at many bridge sites, and there are quite a number of bridge sites where basically the design guidelines were followed, and despite that, there were lots of problems reported in terms of local scour developing, okay? Despite the fact that in principle it shouldn't. And what are the possible reasons for this thing happening? Well, the main reason is that the set of of lab experiments based on which these formulas were proposed have some limitations. And they are mostly related to the limitations of the flumes in which these experiments are conducted. Because you cannot go in terms of the scaling of these experiments to a too high scaling factor, you know, then it means that, for example, if you do a compound channel, you cannot have the width of the floodplain to be very large, despite the fact that in the field you can have rivers which are with a very large floodplain. Then another big issue is the fact that despite the fact that in principle bridges should always be positioned in a region where basically the banks are parallel and also the channel is relatively straight, unfortunately there are most of the bridge sites are positioned in regions where at least the channel curvature is basically under the category mild to medium. And even with a mild curvature, you start having an acceleration of the flow toward the outer bank, which means that basically you are going to get more severe scour at the outer bank abutment. And unfortunately, all the existing design guidelines were developed based on experiments performed with straight channels. And this is because in the existing flumes, it's very tough to basically have enough width such that you can basically have something which resembles as a curved channel, okay? So all the existing design formulas were developed for straight channels, but when we apply them at field conditions, we apply them for situations in which curvature effects are not necessarily negligible, okay? So what is our proposed approach? We basically are advocating a numerical approach in which we are going to replace the data obtained from those scale model studies by data obtained from three-dimensional Reynolds average Navier-Stokes equations, okay? And the advantage of performing numerical simulations today, or because we have relatively fast computers and we have advanced turbulence models and these models are relatively accurate, of course we need to validate, okay? It is the fact that in terms of the numerical model, it is not much more expensive to do a simulations in which we have the bridge in a curved channel as opposed to a bridge in a straight channel. We can very easily basically modify pretty much any geometrical parameter we want, including the width of the floodplain. This can be relatively easily done, which is not the case when we are going to try to do experiments. So basically, at the end of the day, the advantage of our proposed approach is that we can consider a wider range of geometrical and flow parameters, based on which we are going to propose new design formulas which should work even outside of the typical range which was used in the flume experiments, based on which the existing design formulas were proposed or calibrated. So as far as the objectives, so of course we have to basically be able to propose an approach, we have to validate that approach, but then basically we want to basically to basically address two issues. The first one is to answer the questions, are the existing design formulas conservative enough for cases in which the geometrical and flow parameters are outside of the range based on which those formulas were originally proposed, okay? And then if the answer is negative, and I anticipate that the answer will be negative, we would like to basically propose new formulas which can be used for effective protection against local scour at wing wall and spill through abutments. So let me start with the work which we did for wing wall abutments. during the first 2 years of the project. So first of all, this is a picture of a typical wing wall abutment, and the main thing you need to recall about any wing wall abutments is that the faces of the abutments are perpendicular to the riverbed, and also the fact that the abutment extends up to pretty much the transition region between the floodplain and the main channel. In fact, the toe of the abutment, the extremity of the abutment, gets just a little bit inside of the main channel. And this is going to be contrasted with what happens at a spill-through abutment, okay? And that's going to be discussed later on. So first of all, wing wall abutments are mostly used for small bridges, but also for small to medium-sized bridges, mostly double-track railroad bridges, as you can see here, or two-lane highway bridges, okay? So here it is a picture of the abutment, which we are going to use in our series of numerical experiments. The geometry of the abutment is basically corresponds to some very detailed laboratory experiments performed at the University of Auckland in New Zealand. However, those experiments were part of a US NCHRP project, okay, because they were done in Auckland because they have some of the largest flumes. And basically this data, it's one of the main data sets which is used by the community, which is interested in local scour around wing wall abutments, okay? And then we place this abutment into a compound channel, very similar to what was done in the experiments, okay? And you can see also here the position of the riprap apron, which is basically supposed to protect against erosion developing inside of the main channel where the velocities are relatively large. And basically you expect the erosion to happen in the contracted flow region containing the abutment on the left-hand side, which is shown here, and also on the right-hand side of the channel. We performed series of experiments for the case in which the floodplain width is equal to 0. So basically there is only the main channel and no big floodplain. And then with a floodplain width of 0.4 meters corresponding to the lab experiments. And then we also performed another series of experiments with a much larger floodplain width of 1.4 meter corresponding to the numbers which you will see in a flume study, okay? You have to multiply by about 20 in order to get the numbers at field conditions. So basically, you can see here the whole channel with the two abutments on the right and the right and the left floodplain, and the two aprons protecting the toe of the wing wall abutments. So the procedure is as follows. We consider a certain geometry. We consider a certain set of flow conditions, let's say a certain water depth. And then what we are going to do, we are going to start increasing the mean velocity or the discharge. And for each value of the discharge, we are going to perform a simulation. We are going to get the bed shear stress distribution over the whole channel bed, and in particular over the riprap region. And this is basically an example of this bed shear stress distribution over the riprap apron. And then we are going to read the maximum value, which in this case happens near the upstream edge of the toe of the abutment. And then for a given riprap size, we are going to use a certain procedure. Is basically due to, it was proposed by Melvin and Coleman, okay, based on experimental studies. And they basically will tell us for this riprap sediment size, what is the maximum bed shear stress for which the particle will resist entrainment, okay? And let's say that our maximum value is smaller than that threshold value. So then what we are going to do, we are going to increase the discharge, we are going to perform a new simulation, and we are going to do this series of simulations until our maximum bed shear stress is going to be very, very close to that critical value. And that's going to allow us to determine the critical mean velocity based on which we can calculate a Froude number, which is just a non-dimensionalization of the velocity. Most of the sediment most of these riprap sizing formulas are presenting the information in terms of this critical Froude number. So here we basically have a diagram which shows you the ratio of the D50 will be the median diameter of the riprap divided by the flow depth inside of the main channel YM versus the Froude number, okay? And let's look first at the experimental results. So let's say that we are at a series of experiments performed with D50 over Y close to 0.4. So they performed such an experiment with a certain velocity inside their flume, and they observed that for this velocity or this Froude number, there was no entrainment of any of the stones which are part of the riprap apron. So this is why in the experiments, based on the experiments, they put this black field symbol, okay? And then what did they do? They increased the velocity or the Froude number, and then they observe if riprap stone is going to be entrained or not, and even here is not going to be entrained. And then they perform a third case, still no entrainment, but then for the fourth case, they observed that riprap stone was being entrained into the flow. So it means that at that point, the shear, the stone was basically subject to shear failure. So it means that a good design formula will give you a prediction between this point and this point. And then they did several other series of experiments with smaller values of D50 over YM. And always for us, what's important is if we are in between the field symbols and the open symbols, okay? So what we did next was to do exactly the same thing, but using our numerical experiments and to come based on our numerical simulation with the critical value, with the critical Froude number where shear failure is going to be observed. And these cases from this data from the numerical simulations correspond to the red squares. And you can see that for all these 5 series of simulations, our red symbols are in between the black field and the black open symbols, which means that all our predictions are consistent with the experimental data. Okay, so this is a very, very important thing because this shows that our numerical methodology basically predicts a shear failure consistent with the experiment. Now, there are 2 other lines which are plotted here, and they are due to 2 of the design formulas which are in the present standard or design specifications used by the state DOTs, which are the formulas of Lagasse et al. And the formula of Pagan-Ortiz. So let's take a look first at Lagasse et al. Formula, which is the blue curve. So let's see if the blue curve is in between is consistent with the data from the experiments. So you can see that if you look at my cursor, you know, at this position, we are in between the field symbols and the open symbols. That's okay. Similar here, similar here. It is only here that the Lagasse et al. Formula is a little bit toward the right, okay? But overall, Lagasse et al. Formula is also consistent, at least for this set of experiments, with the experiments conducted by Melville, okay? Let's now take a look at Pagan-Ortiz formula. You see that Pagan-Ortiz, it's okay for this data set. It's at the threshold, but still okay for this data set. But you can see that for D50 over YM 0.25 and for D50 over YM 0.4, the green line is toward the left of the region, which is the region where more or less shear failure is going to occur. Which tells you what? It tells you that this formula, in this case, it is too conservative, okay? So based on these results, we can say that our numerical results are basically giving good results, but also Lagasse et al. Formula, it's also giving quite reasonable results. So now let's see what's going to happen if we are going to do those simulations with a much larger width of the flat plane. So this corresponds to these symbols, these 3 green triangles. And you can see that these 3 green triangles are situated to the left of both the Lagasse et al. And of Pagan-Ortiz, which means what? Which means that we are if we have a Froude number larger than this value, if we are in this region, already we are going to have shear failure. However, both these 2 design formulas will tell us that there is no problem. And obviously there is a problem. Okay, so you can already see from our data that even though we are applying this design formula just for straight channels, where this formula should give us conservative estimates, that doesn't happen once the flat plane width increases quite a bit. Okay, so basically we will need some new design formulas which can fit all this data, okay, including for cases in which the flat plane width is larger than what is typically used in the experiments based on which those formulas were calibrated. The other issue is that, as already mentioned, all these design formulas were based on flume experiments performed in straight channels, or on most bridge sites, there is some channel curvature. So basically, we are also going to perform a series of simulations where we are going to gradually increase the channel curvature. And in particular, the range of relevant values are between a ratio between the radius of curvature and the width of the main channel of 20 and something which goes to infinity, which means straight channel. Just to basically show what happens for a channel of very high curvature, we also run a series of simulations with a ratio between the radius of curvature and the width of the main channel equal to 2, though again there are basically no bridges which are situated in a region with R over W equal to 2. But there are plenty of bridges which are situated in channels with a curvature in this range. So basically, this is the matrix of simulations. You can see that we basically varied the flat plane width BF, okay? We varied the radius of curvature, and we also varied the diameter of the riprap stone. Typically, the range was between 20 millimeters and 61 millimeters. So now, what's happening in terms of the flow pattern? So here we are looking at the velocity magnitude, and we are looking at the 2D streamline patterns at the free surface. And you can see on the left the case of a straight channel. Then on the top right, we have a case of a channel of mild curvature. And then at the bottom, we have the case of a channel of very high curvature. And you can see that if the channel is straight, first of all, the flow patterns and also the streamwise velocity distribution is quite symmetrical, you know, with respect to the center of the channel. But once basically we have curvature, then you are going to have higher velocity at the free surface, but in reality over the whole water column at the bank, near the outer bank, and in particular near the abutment situated at the outer bank. And the other effect is going to be that the length of the recirculation region forming downstream of the outer bank abutment is going to start being larger than the one forming at the inner bank, okay, for the inner bank abutment. In terms of the bed shear stress distribution, the main thing to observe here, so basically what we did, we are basically plotting the bed shear stress distribution over the riprap apron, and basically these are the results obtained for the straight channel, and these are the equivalent results obtained for the case in which the channel curvature is relatively mild. And we are showing the distribution starting with a relatively smaller size of the riprap stone going to a larger size of the riprap stone. And you can see that in all these 8 cases or 8 simulations, the maximum values always occurs at the upstream edge of the abutment. And indeed, if you all the laboratory studies of local scour performed at wing wall abutments show that local scour basically starts developing in this region. However, one important observation is that there is a second region of relatively high values, which typically develops only for relatively large median diameters of the riprap stone. And this region is situated basically more away from the toe, from the extremity of the abutment. So basically you have a second high bed shear stress region here. However, the peak values here are still about 30% lower than the absolute peak values which are observed near the corner. So now let's see how we can develop a new design formula. So for this, I already basically showed you some results obtained using the 2 formulas which are basically recommended by the present specifications in HEC 23. And these 2 formulas can be put in a non-dimensional form. as follows. So basically, d50 over y is going to be to a constant at a certain power multiplied by this critical Froude number at another power. You can see that in both formulas, even though the exponent of the Froude, for the Froude number is different, so it's equal to 2 for Lagasse et al. And 1.62 for Pagan-Ortiz, the power exponent of this coefficient, it's always half of the power exponent of the Froude number. So 1.62 divided by 2 is 0.81, 2 divided by 2, it's equal to 1. SS here is the specific gravity of the riprap. So in fact, you can basically write both formulas into the following generic relationships: d50 over y equal to a constant at power alpha over 2 multiplied by the critical Froude number at power alpha, with C 0.645 and alpha 1.62 for Pagan-Ortiz and 0.618 and alpha equal to 2 for Lagasse et al. The main observation here is that in both design formulas, even though C and alpha are different, they basically remain constant. Okay, so it doesn't matter what are the flow conditions, what is the geometry of the channel, the geometry of the abutment. When you apply these formulas, you apply them with a constant C and a constant alpha. So our idea is the following. What if we are going to allow the C and alpha, which rather than being constants are now free parameters, to be a function of the main non-dimensional geometrical parameters? And in the case of a wing wall abutment situated in a curved channel, then the two main geometrical parameters will be the flat plane width, or the non-dimensional flat plane width, and the channel of the radius of curvature, or the non-dimensional radius of curvature. So this is going to be our approach. So now, why do we need that? And I'm going to the previous slide. So here, basically, I'm showing you results obtained from the series of numerical experiments which we performed. And also, we represented the formula of Pagan-Ortiz and the formula of Lagasse et al. And you remember that for a design formula to give conservative estimates, then the data have to be at the right, on the right of that curve. So you can see that if we consider Lagasse et al., you can see that basically there are no points which are situated to the right, which means that Lagasse et al. Equation is basically not conservative enough pretty much for all the test cases which we consider. Now, if you look at Pagan-Ortiz, you can see that Pagan-Ortiz is sufficiently conservative for about 1/3 of the data, but 2/3 of the data, again, even Pagan-Ortiz formula is not conservative enough. Now, a lot of these points correspond to channels which are not straight. So to be honest, we do not expect Pagan-Ortiz formula to be conservative enough for the test cases in which the channel, the radius of curvature was not infinity, okay? But the problem is, can we develop a design formula which is going to relatively be able to predict these values of the critical Froude number? So in order to do that, what we did first, we plotted in log scale d50 over y versus the critical Froude number for all the test cases which we performed with different values of the medium diameter of the riprap stone and various radius of curvature, but we maintain the flat plane width to be constant. So here I'm showing you only the results which we performed with a flat plane width of 0.4 meters. And you can see that for each radius of curvature, we get a series of points with different diameter of the riprap, and we can fit a line. What do we mean that we can fit a line? It means that indeed a relationship of the type d50 over y is proportional to the Froude number at a certain power, meaning power law is a good way to basically describe the variation of d50 with the Froude number. More than that, if you look at the different lines, you can see that these lines are parallel to each other, which means what? Which means that the power exponent for the Froude number has a value which is independent of the radius of curvature of the channel, which is a very interesting result and also a very good result in terms of having a methodology which can be easily applied. Okay, so we can basically look at the slope of these parallel lines, and this slope corresponds to a value of alpha 1.67. So you can see that for BF equal to 0.4, we can basically fit very well all our data sets, you know, if basically alpha is equal to 1.67. Okay, so you can see that this value is not exactly equal to alpha equal to 2 in Lagasse et al., or to the value of alpha in Pagan-Ortiz formula, but is within that range. And in fact, we basically did this exercise for all the three values of the flat plane width. And you can see that if we do that, these predictions of, let's call the new design formulas, they are basically fitting all our data points very, very well. And again, here the main result is that alpha is a function only of the flat plane width, while the constant, the other model constant C, is basically a function of both of the flat plane width and the radius of curvature. And in this table, we are basically summarizing the values of alpha and C from the different series of simulations performed with different radius of curvature. Here we are giving the non-dimensional radius of curvature R over W, and with different values of the flat plane width, or equivalently the ratio between the flat plane width and the width of the main channel. So if you look at our range of alpha, alpha goes between 1.62 and 1.84. This is within the range given by Pagan-Ortiz formula 1.62 and Lagasse et al. 2. Okay, so this looks very reasonable. More than that, for the C coefficient, if you look at the cases corresponding to a straight channel, and if you look at the values of the flat plane width, which are relatively small, which is basically the type of data which was used to calibrate those existing design formulas, then the values of C are 0.48 and 0.6, which are very similar to the 0.646 and 0.618, which are used in the formulas of Pagan-Ortiz and Lagasse et al. So you can see that our results, our values of the parameters are relatively close to these two design formulas, as long as we are using data sets which are consistent with the laboratory experiments based on which those design formulas were calibrated. So with this, let me show you some of the results which we obtained during this year for spill-through abutments. And you can see that the main difference between a spill-through abutment and the wing wall abutment is that the toe of the abutment, the lateral face of the toe of the abutment, basically is inclined. Okay, and also in general, the abutment length is smaller than the flat plane width. So basically, the lateral face of the toe of the abutment connects with the riverbed over the flat plane rather than very close to the main channel. Okay, and this of course has lots of implication in terms of the flow pattern and in terms of the distribution of the bed shear stress around the abutment. So again, here are some other pictures of abutments, and you can see what happens at high flood conditions, where basically part of the abutment was washed up by the flow. And I should also mention that as opposed to wing wall abutments, which are generally used only for small bridges, spill-through abutments are basically used over the whole range of bridge sizes, going from small bridges to medium and large bridges. So again, as far as the geometry of the specific spill-through abutment, this was basically taken to be identical to the one used in a series of experiments performed at the University of Auckland, again by Melville, as part of another NCHRP project. And basically, we just took the geometry and we put it in exactly the same compound channel, which we used for the wing wall abutment work, which I just described before. Here we are given a description of the series of simulations. So basically, we run simulations with 4 values of the flat plane width, going from 0.5 meters to 2 meters. The the median diameter of the riprap was either 20 millimeters or 40 millimeters, and then we performed simulations with various values of the what we call the relative length of the abutment, which is the ratio between the abutment length and the floodplain width. So it's the ratio between LA and BF. Okay. And LA over BF can basically vary typically between 0.2 and 1. Okay, so when LA over BF is equal to 1, it means that the spill-through abutment extends until the main channel, very similar to a wing wall abutment. Okay, and additionally, we perform simulations not only in straight channel but also in curved channels. Now, in the presentation today, I'm not going to show you the results obtained in curved channels. Okay, this is something which we are still working on, and we hope to finish by the end of the year or maybe start of next year. But we already basically did all the work for the case in which the spill-through abutments are situated in a straight channel. Here is a picture of the computational mesh. You can see that we have a very fine mesh around the abutment, and in particular in the regions where basically the flow is highly three-dimensional. So an observation as opposed to spill-through abutments where basically the flow of the free surface is a relatively good indicator of what happens over the whole height of the water column, the flow is much more three-dimensional in the case of a spill-through abutment because of the angle of inclination of the lateral walls of the abutment. So here we are basically showing you again the velocity magnitude of the free surface, and then we are also showing you the distribution of the bed shear stress. And you can see that there isn't basically a one-to-one correspondence. You can see that the largest velocity does not occur, velocity amplification does not occur really around the edge of the abutment or the toe of the abutment. It rather occurs the region next to the abutment, but which corresponds to the transition between the floodplain and the main channel. And that makes sense because you would expect the maximum velocity to be situated in a region where the flow depth is higher, because according to Manning, higher flow depth means higher velocity. Okay. However, when we are looking at the bed shear stress, also because the riprap size is larger, so the roughness is higher, the peak values of the bed shear stress are still obtained near the junction line between the lateral side of the abutment and the floodplain. So indeed, for these cases, performing something like 2D depth average numerical simulation is not a good idea. You should not expect those predictions of the bed shear stress to be accurate. So here we are showing the results, again, the same diagram, the 50 over Froude number, for all the test cases which were conducted in a straight channel are equal to infinity. We are also basically plotting the Lagasse et al. And Pagan-Ortiz formulas, but be very careful here. These are formulas which are due to the same groups, but these are formulas from a totally separate set of experiments performed for spill-through abutments. So these are not the same values which we were using for wing wall abutments. Okay, and we are going to discuss in 1 second what are the values of the power law coefficient and of the constant for these two design formulas. But again, here we are talking about straight channel simulations, and the question is, are these design formulas conservative enough? And here you can see that Pagan-Ortiz formula is basically not conservative enough for any of these data sets. Lagasse et al. Formula works quite well for about 3/4 of the data. However, there are still a certain number of test cases for which the critical Froude number is smaller than the one predicted by Lagasse et al. Formula. And these test cases typically correspond to the ones in which we have high values of LA over BF, meaning the abutment length is relatively close to the floodplain width. For these cases, we get basically values which for which the critical Froude number is smaller, maybe by 10–20% than the one basically predicted by Lagasse et al. Formula. Okay, so still there is a need to improve these predictions. So here are again the equations for the Pagan-Ortiz and Lagasse et al. Formulas for spill-through abutments, and you can see that as opposed to wing wall abutments, the coefficient of the power law coefficient for the Froude number given by both formulas is equal to 2. So then the coefficient here is going to be at power 2 over 1 power 1. And the value of the constant are going to be 0.324 for Pagano-Ortiz, 0.54 for Lagasse et al., and alpha is going to be equal to 2 for both of these formulas. So now let's see if we are going to basically try to develop a design formula which retains the same functional relationship, but in which alpha and C become free parameters as opposed to constants. Can we basically fit all our test data? And the approach is very similar to what I already discussed for Winkel abutment. And you can see that if we do that, and this corresponds to these color lines, we can basically fit pretty much all the points obtained from those numerical experiments. Again, we can see another interesting result is that as far as the value of the power law coefficient, this value of alpha, you can see that as we increase the relative length of the abutment, but if we maintain the width of the abutment, excuse me, the width of the flat plane the same, these lines are parallel to each other, which means that the value of alpha is a constant. However, the value of alpha is a function of the flat plane width. And for example, for a flat plane width of 2 meters, alpha is equal to 1.7, which is not the alpha equal to 2, which you have in the two design formulas. And on the next slide, we are basically summarizing the predicted values of alpha and C. And there are basically two main comments here. So first of all, let's look only at results for which L over B is smaller than 1. Meaning the whole apron is situated over the flat plane and no part of the apron is situated over the transitional region or over the main channel. In this case, you can see that alpha is only a function of the flat plane width. And as the flat plane width increases, alpha decreases. So for small values of the flat plane width, alpha is very close, 1.95, you can see here, very, very close to the alpha equal to 2 in the existing design formulas. But as you go to a larger width of the flat plane, you need to basically start reducing the alpha in order to be able to fit the test data. The other important observation related to the values of alpha is what's happening when L over B equal to 1. For L over B equal to 1, our data shows that alpha assumes a constant value, which is independent of the flat plane width, and that value is equal to 1.85. So the main message here is that you need to lower alpha for large flat plane width, and then you should be able to get good predictions for all the test cases. So with this, let me go to conclusions. So basically, our study have shown that the existing design formulas in the HEC 23, which are the design specifications, are not conservative enough once these formulas are used for conditions outside their calibration range, in particular for large widths of the flat plane, and also they do not account for the effects of the main geometrical parameters defining the flow, such as the flat plane width or the relative abutment lengths in the case of spill-through abutment. In our numerical approach, we basically, main advantage of this approach is that we are reducing the need for expensive and comprehensive laboratory experiments. We, of course, need some laboratory experiments to validate our approach, but once the approach is validated, it is quite easy to apply it for cases which are very, very expensive to basically to perform experiments for them in the lab. And in particular, this is the case for the case in which you have the bridge situated in a region of medium bank curvature. So what is the end result? The end results are these design formulas which can be applied for a much wider range of the main geometrical and flow parameters which are encountered in the field, which means that in the end we are going to have more reliable approaches to protect bridge abutments against local erosion, against local scour, and that basically should result in it's going to have lots of economical repercussions, because you are not going to have, if you do this design properly, you are not going to have to go all the time and put more riprap and redo the riprap protection, after every major flood. So as far as the main outcomes, we develop a 2-parameter design formulas for wing wall abutments, which can be incorporates the effect of the flat plane width and channel curvature. And as far as spill-through abutments, at this stage, we also develop a 2-parameter design formula, which was proposed for, which can be incorporates the effect of the flat plane width and the relative length of the abutment. And at the present time, we are also working on including the effect of channel curvature. So at the end of the day, we hope to have a formula which can be used both for straight channels and also in channels of relatively large curvature. So with this, I would like to conclude my presentation, and I will be happy to answer any questions if we have enough time. Thank you very much.
Well, thank you, George. That was great. We do have some time for questions if anyone wants to either put them onto the chat or to ask George directly. George, I did have one question for you. So I was wondering how you're going to implement this. Is this getting put out into the field now in Iowa? Or another location?
Obviously the first step will be an obvious one. We are going to publish this work. In fact, the work on wing wall abutments is already in press, and we hope to submit a second paper on the formula for spill-through abutments at the start of next year. But really, basically, our implementation plan is to basically be in contact with the subcommittee, which is in charge of new research briefs for HEC 23, and basically what we would like to achieve is to include these new formulas in a future FHWA technical brief to HEC 23. And basically, probably once this generic design formula for spill-through abutments is completed, we basically are going to be in contact with the hydraulics labs at FHWA. So basically with Cornel Kearney, who has also done lots of work on local scour, and he's also a member of the subcommittee, and we are going to try to have some discussions with the subcommittee and see if they are interested in basically working with us to develop a technical brief.
Great. And I think there's a number of students on the call, and I think could you give the students an idea of how long these changes make to code? Because we always talk about implementing our research, but there is a process to it. So if you could talk to that, I would appreciate it.
So just to make sure that I understood correctly your question. Your question was, what is the time needed to modify the code to perform the simulations, or something else?
Yeah, it's sort of. So in terms of getting it implemented, you spoke correctly, right? You have to get it into the codes, you have to go change it, you have to get everyone's agreement. And I think a lot of times students think, oh, we do the work and then we can go implement it right away. And I was just wanting to get your experience on how long you think it'll take.
Yeah, so again, performing something like a matrix of about 30-40 simulations with these 3D numeric 3D codes, and we are using a commercial code. It starts with CM+, but you can use something like Fluent or any other of the major CFD codes. I will say that it takes at least 6 months to run the simulations. But then also, basically, you get into the issue of setting up the model properly. And one major issue for us was the very high values of the roughness over the riprap apron. Most of these numerical models work very well with relative small to medium values of the roughness. Once you go to very high roughness, some of the models do not work very well. So we need to basically do lots of calibration, lots of validation, even for much simpler cases, to make sure that we get values of the bed shear stress which are consistent with the values of obtaining, let's say, in a fully developed turbulent flow in a channel for which the bed has a certain roughness. Okay, but just to understand, once we perform all these simulations and once we analyze the data and we were able to feed those curves to that data, okay, and to get the values of alpha and C, at that point we have all the information which is needed for a practitioner engineer working for the Iowa DOT to do the design. Because once we have this formula, they do not care about how the simulations were performed or anything like that. They just care about that table, and that information can be basically presented as a table, or it can be presented as in a graphical way to do basically the interpolation for the two model coefficient alpha and C. And all what research of a practitioner engineer has to do, they just basically have to interpolate the values of alpha and C, and then exactly like for the design formulas which are in the present standard, they have to get a prediction for the median diameter of the rock riprap. Okay, and that's all what it is. So it is very easy as far as being used by the people at the state DOTs. Okay.
Great, thank you. Yeah, I think we have a lot of these issues, you know, in anything, structures or transportation or water, and is getting the work implemented, right? We have the formula, making sure that it works, getting it out to the engineers. I think sometimes we think it goes very quickly, and actually it takes a lot of work, as you've shown today. So I appreciate the answer. We have time for another question or two if anyone wants to ask. Okay, George, I don't see anything on the chat, or I don't hear anyone.
This is what I wanted to ask you, because I cannot see my chat. I think I have to stop sharing the screen to see my chat.
Okay. So anyways, thank you very much for giving an excellent presentation. I want to wish everyone a good weekend and stay safe. And George, thanks again.
Thank you very much.
Appreciate it.
Thank you very much for the invitation. I greatly enjoyed it.
Good.
See you.